Alright, let's take a look at well, you have seen this animation in the last class. When this particle executes simple harmonic motion according to the equation y equal to a sine kx minus omega t or plus omega t, depending on whether the wave is advancing to the right or to the left. Is that right? Let's have a look at that one more time. You can see as the particle vibrates up and down, the wave advancing to the left will be a sine kx plus omega t, and the wave advancing to the right will be y equal to a sine kx minus omega t. Okay, now that is a harmonic wave. Let's do a couple of problems. The wave yxt, you see that? Y, the displacement as a function of x and t. So the equation for a harmonic wave is actually a function of x as well as time. Yxt equal to a cos k times x plus 34t. You can see this is a cosine function. What does it tell you? A function can be sine function or a cosine function. The wave function will be a sine function if at t equal to 0 the particle is at the equilibrium position. If the particle is at the upper extreme when t equals 0, then the equation will be, there will be a phase difference of pi by 2. That will make the equation a cosine equation. So the wave yxt equal to a cos k times x plus 34t represents a traveling wave, advancing wave, where x is in meters and t is in seconds. What are the direction and the speed of the wave? There's nothing to calculate here. Just look at the general equation. If you notice, the equation, the general equation of a wave will be yxt is a cos k times x plus vt. You see, when the k is outside, this is of the form k times x minus vt or k times x plus vt. You must look at the specific form of the equation. So this tells you that this is a wave advancing to, is it to the right or left? To the left. And what is the speed of that wave? It's 34 meters per second. This is v, the speed of the wave. The sine function or cosine function only determines the initial state of the wave. In other words, where is the particle when you start looking at the clock? The wave yxt equal to a sine k times x plus vt is a wave traveling to the left with a speed v. So it doesn't matter whether you have a function given as cosine function or a sine function. So the wave yxt equal to a cos k times x plus 34t is a wave traveling to the left with a speed of 34 meters per second. So when you are given the equation of a harmonic wave, a lot of information about the wave are actually contained in the equation. Let's now look at another problem. At time t equal to 0, the shape of a wave pulse yx0 is described by this equation. This time the equation is not a sine function or a cosine function. It's simply a rational function. It is 0.2 meter cube divided by 2.5 meter squared plus x squared, where x is in meters. Plot yx0 versus x and give the general wave function yxt at any time t for a pulse that is moving in the positive x direction with a speed of 10 meters per second. And 2, the equation for a pulse that is moving in the negative y-x direction with a speed of 10 meters per second. You see, if this is the general equation of a wave pulse, how would you make it appear as a wave equation that describes an advancing wave, whether it is advancing to the right or to the left? For a wave that advances to the right, what all we need to do is replace x by x minus vt. And for a wave advancing to the left, replace your x by x plus vt. Alright, first I have drawn that on my calculator. You can also try drawing this on the calculator. You can use the x scale as negative 10 to 10 and y scale. If you know how to look at a function, you can see what is the maximum value of y that you can get here. You see, the maximum value of y occurs when x equal to 0, and that maximum value will be 0.2 divided by 2.5. So you can actually draw a graph on your calculator by putting this on your graph window and choose the window x value negative 10 to 10, y value from 0 to 0.1. That's right. And you will get a pulse like this. So look at the beautiful wave pulse that is represented by this equation. And now, if this is a wave pulse advancing to the right with a speed of 10 meters per second, how will this equation be modified? What do? Replace your x by x minus vt. If this is a pulse advancing to the left with a speed of 10 meters per second, to represent that, you replace your x by x plus vt. Alright. At t equal to 0, the shape of the wave pulse we just saw. If v equal to 10 meters per second, for a wave that is traveling to the right, we replace x by x minus vt. Therefore, this is the equation for the wave pulse that is advancing to the right with a speed of 10 meters per second. And a wave that is advancing to the left with a speed of 10 meters per second, we replace x minus 10t by x plus 10t. So this is the equation for the wave that is advancing to the left. Another problem. A harmonic wave with a frequency of 60 Hz and an amplitude of 0.2 meter travels along a string to the right with a speed of 10 meters per second. Write a suitable equation for this wave. Well, you are given the speed of the wave, you are given the amplitude, you are given the frequency. Alright, what is the general equation? You can start by writing this general equation. Y equal to a sine k times x minus vt. Isn't that right? Well, where k is 2 pi by lambda, v is the wave speed, a is the amplitude, and so on. Well, can you obtain these values? What is the other form of the equation? The other form of the equation is y equal to a sine kx minus omega t. If you distribute this k, just distribute that k. Distributing the k, you get y equal to a sine kx minus kvt. And what does kv equal to? Do you remember what kv is? K is 2 pi by lambda, and v, 2 pi by lambda times v is actually 2 pi times f, that is omega. So the equation is therefore y equal to a sine kx minus omega t. So you must understand this equation and the equation I wrote earlier are the same equation. Okay, let's start this problem. We got frequency f equal to 60 Hz, amplitude a equal to 0.2 meter, and speed v equal to 10 meter per second. The general wave function for a wave traveling to the right is, alright, yxt equal to a sine k times x minus vt, which is the same as kx minus omega t. Alright, now we have v equal to f lambda. That means lambda equal to v over f. You see, we have v here, we have f, and therefore we can find lambda. Lambda equal to 10 meter per second divided by 60 per second, that is 1 over 6 of a meter. That is the wavelength. That means we can now come and find the value of k. What is k equal to? K is 2 pi divided by lambda. That will be 2 pi divided by, what is lambda? Lambda is 1 over 6. 2 pi divided by 1 over 6. The 6 will go up and multiply with 2 pi, giving you 12 pi. Hope you understand that. K equal to 2 pi divided by 1 over 6. That will be 12 pi. So we now know the value of k. We know the value of v. We can now write the equation for that harmonic wave. That will be yxt equal to 0.2 sine 12 pi times x minus 10t. Look at that again. A sine k times x minus vt. Alright? So information about a wave can be used to write the equation of that wave, which is the same as, look at the way, distribute that 12 pi, you get that will be 0.2 sine 12 pi x minus 120t. This now is of the form yxt equal to a sine kx minus omega t. What is omega equal to here? 120 pi. So this is of the form a sine k times x minus vt, which when you distribute, you get the form kx minus omega t. In other words, k times v is omega. Another problem. A wave function for a harmonic wave